So, I mean, there aren't going to be any revelations about it. Just we should probably do a few more complicated examples. We should probably see examples where the ratio test gives divergence, or examples gave convergence yesterday. We should probably see how the ratio test can fail, or stuff like that. And let's see, this leaves us with kind of a string of examples. Let's look at a divergence example first. Obviously, giving away what the answer is. This series looks divergent. And it looks divergent to me because, I mean, we've got an exponential in both the top and the bottom, but 9 to the n is going to be a heck of a lot bigger than 2 to the n, or negative 2 to the n plus 1, as the case may be. And that n down there, I suspect, isn't doing much of anything compared to how big 9 to the n and 2 to the n are. In fact, just looking at it, my bet is that if we could take the limit as n goes to infinity, we would find that this diverges by the nth term test, and we wouldn't have to do anything fancy. You know, the issue is that if you try to take that limit, it's not at all easy to do. If we try to take this limit, we're going to need L'Hopital's rule. We're going to need the product rule when we take the derivative down there, and it's just going to get worse and worse as we take its derivative rather than simplifying. So if we really want to properly investigate this, we might try the ratio test. And I mean, I say the ratio test. The ratio test is kind of the default test when you have powers and when you have factorials. So no factorials here, but we do have powers. And really, it's not clear quite what else we'd use. I mean, we can't use the limit comparison test because the terms are not always positive. We could whack absolute values around it and try to use absolute convergence. But sometimes, even though this is a kind of messy looking expression, and these a sub n plus 1s and a sub n's are going to make a kind of messy fraction, it's probably easiest in the end to just brute force this with the ratio test. And if the ratio test fails, well, then we can try something else. So we're replacing n with n plus 1. So I'm going to edit that. But just to be clear what's happening, we're replacing n with n plus 1, and then those 2 plus 1s are going to become a plus 2. Here's an n plus 1. And then down here, we've got the terms of the series. These are all in absolute values. Yesterday, the absolute values never actually did anything because the examples we looked at were all positive. Here, it's important that we remember them because we've got negative stuff floating around that the absolute values are going to get rid of. And now this is so messy, we probably want to just go to a new frame. So we're dividing by a fraction, so we're going to flip that and then multiply it. And eventually, we're going to take a limit, but it's no use worrying about the limit right now because this is so messy that we couldn't possibly take the limit as n goes to infinity. That would be a disaster. We'd be using L'Hopital's rule, and we'd be using the product rule multiple times in both the top and the bottom. So I, of course, haven't forgotten about the limit, but I want to try to get this under control. I want to try to do some simplification before I worry about it. What's going to happen when you use the ratio rule is we're going to get terms in the top and bottom that clearly correspond to one another. I mean, we have a power of 9, a power of 9, and n plus 1, and so on. And we can just break this into 3 fractions and deal with them one after another. 9 to the n plus 1 over 9 to the n. When we've got the same base and we're dividing, we subtract the powers. So we're going to wind up with a 9 to the first. Let me not do anything with that n over n plus 1 for the moment. It doesn't simplify in the way other expressions do. When we're multiplying absolute values, we can break them apart. The absolute value of a product is the product of the absolute value. The absolute value of a quotient is the quotient of the absolute value. That is not true for addition and subtraction, but we don't have addition and subtraction. We have multiplication. So we can do this. And the absolute values are just going to make the negative signs go away. So, -2 to a power, if we make the negative sign go away, we get +2 to a power. -2 to a power, if we make the negative signs go away, we get +2 to a power. And now what happens? Let me think this through. We've got the same base. So we subtract and the n's go away. and we are left with a negative first power. And 2 to the negative first is 1 over 2. So this is just the world's messiest way of writing 1/2. So we've got our 9. Again, when we're multiplying, can bring stuff in and out of absolute values. There's a sub n plus 1 over a sub n, or I guess I should say there's the absolute value of that. And the absolute value isn't really doing anything, not anymore. It's done its work. 9 is positive, 1/2 is positive, n over n plus 1 is positive. We take the limit as n goes to infinity. That's going to 1. Can everybody see that? It's a quick L'Hopital's rule problem. The derivative of the top is 1. The derivative of the bottom is also 1. So this is 9/2, and 9/2 is greater than 1. And the ratio test says that if we take this limit and we get a result that's greater than 1, the whole thing diverges. So this is what I expected would happen. I mean, this is what I said would happen at the start. Again, I mean, it was obviously a certain amount of work. I don't really see a cleaner way of doing it. Again, I mean, what I really want to do is the nth term test. And if I threw that up on Desmos, I could probably see that those terms are not converging to 0. But as far as doing it in an analytical formal proof type of way, I think the ratio test was all we had here. The ratio test, we've seen 2 examples yesterday of convergence, maybe more than 2. We've seen an example today of divergence. The ratio test is powerful, but it's not unfathomable. That's not quite the word I want. It can just fail. I mean, if we get a limit of 1, we get no information. So it's not so much that the ratio test is failing. I mean, it's never giving us the wrong information, but it's not telling us what's happening. Let's look at negative 1 to the n over n squared plus 1. And to me, this doesn't really look like a ratio test question. And you know, whether something looks like the ratio test or not can be a little subjective. But I've said that I like the ratio test for factorials and for exponentials. And I mean, we've probably have a good idea by now of why I like the ratio test for these things. To use the ratio test, we need to be able to do quite a bit of simplification. And exponentials simplify really nicely. We just subtract powers. And we saw yesterday that factorials simplify really nicely. So that's my motivation for saying this. And I look at this, and well, we do have n exponential. We've got -1 to the n, but this isn't, I mean, n squared plus 1. This isn't really exponential. Still, what happens if we use the ratio test? I mean, there's nothing stopping us from trying. And we get one of these messy fractions of fractions, which is always our fate when we do this. And I didn't leave myself quite enough room on the board, so we're a little scrunched. But there's what happens when we replace the n's with n plus 1s. And there's the original expression, the a sub n, leave the n's alone. And we flip the denominator and multiply it. And we get this n squared plus 1. And then down here, we have this mess. I call it a mess. It's not really that bad. It's n squared plus 2n plus 2. If you FOIL n plus 1 squared and then add 1 to it. And then we have, -1 to the n plus 1 and -1 to the n. And we don't have the really nice simplifications that we had, or at least we only have one really nice simplification, which is that those -1s, well, first they turn to -1. N plus 1 minus n, -1 to the first. And then they completely go away because all -1 is doing is turning stuff negative, and we're inside the absolute value, and the absolute value makes everything positive. So, not great simplification, but that's okay. All we need to be able to do is take the limit as n goes to infinity. I mean, you look back and you ask, why did I do all this simplification? It was because if I hadn't, I couldn't have taken the limit. I'd have had, if I tried to use L'Hopital's rule, it would have been a disaster. I'd have had to use the product rule twice in both the numerator and the denominator. So the fact that there's no real simplification isn't the problem. The problem is that when we take the limit of this rational function, Well, we hit it twice with L'Hopital's rule. We get 1. And for the ratio test, 1 is a failure state. And again, it's important not to get these tests confused, because if we were using the limit comparison test, a limit of 1 would be just fine. 1 is a finite number between 0 and infinity. That's what we want when we're using the limit comparison test. But when we're using the ratio test, it's a failure. And if we want to know whether this converges or not, we've got to try something else. And there are a few other things we could try. There are at least 2 other things we could try. Well, I say that we haven't learned one of those things yet. This surely converges. One way we could demonstrate that, in this particular case, we could take the absolute value, and if that converges, the original series also converges. That's a fact we know. We called it absolute convergence. The absolute value makes the negative sign go away. This top is either -1 or +1, depending on what n is. When we have it inside an absolute value, it becomes this. And this is algebraic, and it's screaming out for the limit comparison test. This looks so close to being a convergent series. It comes so close to being 1 over n squared. And when we have that intuition, the limit comparison test is our friend. We take the ratio and again, when I keep saying, it's so important not to get these confused. Here we get 1 again, but this time getting a limit of 1 is not a failure state. Getting a limit of 1 means the limit comparison test works. And since this series converges, this series also converges. And since the absolute value converges, this converges as well. But the ratio test failed here. Again, I sort of why do I do the things I do? I had to take the absolute values because the limit comparison test requires everything to be positive. So if I wanted to use the limit comparison test, I had to do this. And if the limit, well, never mind. That's we've lectured on the limit comparison test already. Compare that to this. This series diverges. I'm not going to try to create any suspense here. We should be able to just look at this and see that it diverges almost immediately. I mean, I say we should be able to. Obviously, you're still gaining experience with this stuff. But the reason I say that, I see this is a rational thing. It's linear over linear. And because the degree of the top and the degree of the bottom are the same, it's going to have a horizontal asymptote other than 0. The limit as n goes to infinity of this is 1/2. And when the limit of the expressions, when the limit of those terms is anything other than 0, it diverges. Nth term test. So there's no mystery about whether this converges or diverges. But what happens if we hit it with the ratio test? Again, this doesn't really look like the ratio test to me because we don't have exponentials and we don't have factorials, and this intuition is going to be proven correct. Give myself more space to write up here. We replaced n with n plus 1, n plus 1 plus 1 became n plus 2. So when we flip the denominator and multiply it, we get an n plus 2 over an n plus 1, and we get a 2n plus 7 over a 2n plus 9. And when we take the limit, absolute values aren't really doing anything, but they're also not hurting anything. The limit of a product is the product of the limits. Assuming that these limits exist, we can just take them separately. And both of these is a less than a minute L'Hopital's rule problem. They're both going to 1. So this is going to 1 times 1, which is 1. And the ratio test fails. So 1 is a genuine failure state. Here we get 1 and the series diverges. Here we get 1 and the series converges. If you get 1, you're going to need something other than the ratio test. And I said we should do some more complicated examples, and we have. I mean, something like this you should be able to do. It's definitely, I sort of like it. The part of me that gets very, excited organizing files on my computer also finds the ratio test quite calming. But it is a matter of just not panicking and keeping track of all of the terms. Like you look at this and it's clearly very messy, but there's nothing here that a college algebra student, at least in theory, would not be able to simplify. Once we flip this and multiply, we just break it up into its component parts. We look at the 9 powers, we look at the -2 powers, we look at the n over the n plus 1, and we just deal with each of those separately. So the ratio test definitely gets you some very messy looking fractions, but again, just don't be overwhelmed. Take them one by one. And I mean, if you're still working on it 10 minutes later, then probably either you have made an algebraic error or the ratio test was not the tool for the job. So that brings us to the end of the ratio test. So the textbook moved stuff around between editions. I believe that the ratio test and the root test get covered in the same section still. So we'll have another test for you tomorrow. And then I'll think about, I'll have to look at what's opened up online, but I'll figure out what we're doing Thursday, and I will see you all Wednesday. I'm sorting out my stuff. I